The following summarizes the Imperial Japanese Empire, scientific research and industrial commitment, to achieve a working uranium bomb, to win World War II. After the stunning victory in the 1905 Russo-Japanese War, Japan embarked on a major expansion of Western scientific technology, to include developing expertise in the new field of atomic physics. The Japanese entry into atomic physics research started in 1911, with Hantaro Nagaoka providing an atomic model. In 1921, Yoshio Nishina, a researcher at the Institute of Physical and Chemical Research, was sent to study in Europe. He studied 2 years under Ernest Rutherford, the father of nuclear physics, in Cambridge, at the Cavendish Laboratory. In 1923, he joined Niels Bohr in Copenhagen. For 5 years he worked on the Bohr theory of the atom. In addition to observing the work performed in Copenhagen, Dr. Nishina visited Göttingen and Hamburg. In 1928 Dr. Nishina returned to Japan. In 1931 he established his own laboratory to research cosmic rays, quantum mechanics, atomic physics, and high-energy proton beams. In 1934, a patent for the apparatus to accelerate ions, a cyclotron, was issued to Ernest Lawrence, from the University of California, Berkeley. Dr. Nishina sent researchers Yasaki Tameichi and Sugane Ryokichi to Berkeley to inspect and learn about the American cyclotron. In Berlin, chemists, Otto Hahn, and Fritz Strassmann, were studying radioactive substances. With a simple table laboratory set up, observed that the bombardment of uranium nitrate, with low-energy neutrons produced barium as a product, rather than radium as they expected. They shared their results with Lise Meitner, who was now living in Sweden, requesting her for interpretation of the phenomena observed during the bombardment of uranium nitrate with low-energy neutrons. Lise Meitner, in collaboration with Otto Frisch, calculated that the lost mass converted into energy, as predicted by Albert Einstein's famous E=mc² equation, and called it nuclear fission. The energy release was enormous. For example, a chemical reaction of hydrogen with oxygen release 5 electron volts per atom. Neutrons moving at a few electron volts bombarding an atom of uranium and bursting it would release 170 million electron volts per atom. In August 1939, Siegfried Flüger suggested the theoretical possibility of exploiting this enormous atomic energy. From the laboratory experiment to the uranium machine. The concept of uranium power results published in numerous scientific journals sent shockwaves across the globe. Researchers in the Japanese Empire who were studying particle acceleration for the past 4 years were especially excited by the concept of nuclear fission. In May 1941, Hagawara Tokotaro, professor at University of Kyoto, presented to the Navy the lecture concerning super-explosive uranium-235. Nuclear research was continued, however. There was little emphasis on a super-uranium bomb since the Imperial Japanese Empire, with its well-trained army and naval units, were victorious across all battle fronts across Asia. With conventional weapons, designed and built in the 1920s and 1930s, the Imperial Japanese Empire expanded to the north, occupying Manchuria and portions of Sakhalin, and to the south, occupying the Dutch East Indies and the northern part of New Guinea, as shown in red. The Imperial Japanese Navy saw the possibility of powering their large battleships with a fossil fuel alternatives extremely interesting, since Japan has no oil. As the third largest navy in the world, fuel demands for 10 battleships, 10 aircraft carriers, and 112 destroyers was enormous. For example, the battleship Yamato alone consumed 70 tons of fuel per hour. Nuclear fission research priority was elevated after the June 7, 1942, Battle of Midway. The humiliating defeat and loss of the Akagi, Kaga, Hiryu and Soryu and the heavy cruiser Mikuma, renewed interest in the super-explosive uranium bomb. The research centers for building an uranium bomb had been established within the physics departments at the universities at Tokyo, Osaka, and Kyoto. Seishi Kikuchi established a Cockcroft-Walton accelerator at Osaka Imperial University in 1933. The physics department at Osaka expanded to support neutron acceleration experiments in a small 0.6-meter cyclotron, which was operational in 1935. In 1935, Dr. Nishina and the Nishikawa group constructed a 0.6-meter cyclotron. The first beam of 3 megavolt deuterons was achieved in 1937. Atomic research at the physics department of Kyoto Imperial University was expanded to include neutron acceleration and uranium bombardment in a 1-meter cyclotron, using a cloud chamber, and a cyclotron. It was determined that 2.5 neutrons are released when uranium-235 was bombarded with a low-energy neutron. This critical data was used to estimate the number of kilograms of enriched uranium-235 needed for an atomic bomb. The greater level of enrichment, the less uranium-235 was needed to achieve critical mass. Uranium is one of the more common elements in the Earth's crust. It is 40 times more common than silver. Although uranium ore veins are common, the uranium content varies. The chart shows typical uranium content variation. No records have surfaced of Japanese uranium ore sources within the newly acquired, occupied territory. It was rumored that uranium sources were in China, Burma and Manchuria. However, comprehensive geological maps were available in 1940 for Japan, Taiwan and Korea. Limited records show that more than 600 tons of low-content, 0.05 to 0.3 weight%, uranium oxide ore was shipped to Japan before 1945. However, the total uranium ore shipped to Japan for enrichment, nor the total uranium ore processed in Korea is unknown. By constructing additional laboratories to develop equipment to enrich uranium-235, which was extremely toxic and corrosive. In addition, uranium consists of 99.3% uranium-238 and 0.70% 235. Since the atomic weight of both isotopes are the same at 92, the enrichment of uranium-235 required separating the two isotopes and discarding U-238. Uranium-235 occurred in a ratio of 1 to 139 in natural uranium ore. Since they were chemically identical, they could not be separated by chemical means. With their masses differing by less than 1%, separation by physical means was found to be extremely difficult. Gaseous diffusion's principle was simple. Molecules of a lighter isotope would pass through a porous barrier more readily than those of a heavier isotope. The tiny weight difference between U-235 and U-238 meant that initial separation would be negligible. Repeat the process hundreds of times in sequential cascades, and the end product would be significantly enriched uranium. Isotope separation using centrifuges, in principle, is simple. However, constructing corrosion-resistant centrifuges, powering cascades of these units, can be challenging. Centrifuge high-speed motors and corrosion effects of uranium hexafluoride require engineering solutions. Thermal diffusion utilizes the transfer of heat across a thin liquid or gas to accomplish isotope separation. By cooling a vertical film on one side and heating it on the other side, the resultant convection currents will produce an upward flow along the hot surface and a downward flow along the cold surface. The enrichment process is slow, requiring a cascade setup of many thermal diffusion units. Electromagnetic separation use large magnetic fields to separate uranium-235 and be collected sooner than the uranium-238. The 8th of May 1945, Captain Rosing, at Bergen, Norway, by order of Admiral Dönitz, instructed Captain Johann Heinrich Feller of U-boat 234 that the war was over, and he should terminate the voyage to Japan and return to Norway. Captain Feller, with officer consensus, surrendered to the Americans, and brought the submarine and its cargo to Portsmouth, after removing the German crew to the USS Sutton. A shipment of 80, possibly 90 cubes, of uranium oxide, each protected by a layer of gold, totaling 560 kilograms, was the cargo headed for Japan. These cubes were approximately 25 cm per side, wrapped in brown paper, labeled U-235. On this secret mission, Japanese officers Genzo Shoji, an aircraft designer, and Hideo Tominaga, a submarine design engineer, were accompanying the cargo of uranium, and disassembled Me-262 jet, and parts for the V-2 rocket. Captain Feller buried officers Tominaga and Shoji at sea, after they committed suicide, with sleeping pills, rather than be taken prisoner. The uranium-235 cargo was omitted from the cargo manifest in the German and American manifest. In addition to the highly enriched uranium, heavy water and benzyl cellulose was also part of the cargo headed for Japan. The finding of nuclear material on U-234 panicked the Americans, who classified the surrender top secret. One major reason the U.S. intelligence service was not aware of the progress of Japanese nuclear energy and weapons development until the surrender of U-234 is largely due to the fact that nuclear researchers and Japanese industrial institutions never transmitted status reports and meeting minutes over military radio channels, which were continually monitored throughout the war by naval intelligence, located in Melbourne, Australia and Hawaii. In 1938, the Japanese implemented a new encryption system for all transmitted military communications, which the Americans called Purple. A few years later, the Signal Intelligence Service reversed-engineered this device and built a Purple decoding machine. Furthermore, as the war progressed, the British Intelligence Service provided limited access to their top-secret code-breaking system called Ultra. The British felt that American security was not stringent enough. After sufficient training, at the British Code and Cipher School, full access was granted. After the surrender of Imperial Japan, the status of the uranium bomb, the city destroyer, is unknown. There are rumors which imply that Japan had an extensive uranium enrichment facilities located within and around Konan, Korea. No inspections were performed by American nuclear inspectors, because Soviet soldiers guarded and prevent entry to Japanese facilities in Korea. This is an aerial overview of Konan, Korea. Today this is known as Hungnam, North Korea. In Konan, the Japanese constructed the largest industrial complex outside of Japan. This industrial complex is linked by railroad to the mineral resources of Manchuria, Korea and parts of China. This industrial city has well-developed harbor facilities for loading and unloading cargo. It is ideally situated for movement of raw materials and products back to Japan. Water from the Chosun Reservoir drives the enormous hydroelectric turbines to power the industries in Konan. The Office of the Supreme Commander for the Allied Powers decided that all equipment related to nuclear activities was to be destroyed. U.S. Army officers and staff inspecting the large cyclotron and ancillary equipment located at the University of Tokyo prior to the demolition of these facilities. Armed American soldiers restricted access to the cyclotron equipment, with 24-hour guards. The physics laboratories were world-class, equal to Western labs. The leading universities had great theoretical scientists and practical engineers, to include several Nobel Prize winners. My research reveals that Japan most likely developed the infrastructure to create nuclear fission reactors, to include rudimentary atomic bombs. However, the American nuclear inspectors in 1945 did not find uranium-235 enrichment facilities in Japan. Or it may also be possible that the tensions with the Soviet Union immediately classified these to top secret, and removed all and any reference to Japanese enrichment facilities beyond Japanese cyclotrons. All related equipment was dismantled piece by piece. Dr. Nishina, shown here, is showing some of the levers used to operate his cyclotron prior to demolition. With numerous chains and pulley systems, the American soldiers were able to move the 100 to 200-ton magnets and steel support from the cyclotron. The rapid demolition of the cyclotrons in November 1945 may be due to the tensions with the Soviet Union, whose intelligence service was keen on acquiring Japanese nuclear technology. The Americans did not want the Soviet Union to have access to any Japanese technology, including the Japanese nuclear weapons effort. The Soviet Union, who controlled all the Eastern European countries up to the border of East Germany, still felt inferior to the superpower, the United States. The Soviet Union needed to build an atomic bomb to be able to match the military power of the United States. The American military were meticulous to remove all components, down to the acetylene torch cutting out portion of the foundations, such that no traces were left. This is the 6th Army Headquarters, in Kyoto, Japan, 24 November 1945. Military personnel are getting into jeeps and drive off to the atomic laboratories at Imperial University of Osaka. These are the images of the Osaka cyclotron and other related atomic equipment. The research equipment required large amounts of electrical power. Dr. Seishi Kikuchi, the leading physicist at Osaka University, is going over papers with U.S. Army officers. American soldiers are using acetylene torch on sections of the cyclotron equipment. Soldiers are attaching a winch cable to part of the equipment through a hole in the building and the cable pulling the cyclotron apart. During the Korean War, the facilities in former Japanese colony at Konan, now known as Hungnam, were bombed. A Canberra Times news article of 28 November 1950 reads as follows. Atom bomb materials were being made at the Gyean Explosives and Chemical Works at Hungnam, on the northeast Korean coast, until it was totally destroyed by superfort bombing. An Air Force investigation team sent to Hungnam after its occupation reported yesterday that the works covered several square miles and were the biggest of their kind in Asia. During the Korean War in 1950, it was rumored that U.S. Marines stumbled across caves outside Hungnam, which contain nuclear facilities, built by the Japanese during the war. In addition, some researchers speculate that the 66 kV power cables, observed by the Marines, were feeding these nuclear enrichment facilities in some of these caves. However, a better explanation is that the 66 kV power overhead transmission lines are providing additional power to the industrial complex in the greater Hungnam area, because hydroelectric power is placed where the water is available from the reservoir. It is easier to run the power transmission lines from the hydroelectric facility to the factories than to relocate the factories to this hydroelectric facility.